G'day. After 2 weeks now, it's still running, which is pretty amazing. I haven't charged it or anything, and it's still running off the same system. It's a little lower. I think it'd probably be running on doing a draw of 10 milliamps at the moment. But still, how much is that, I wonder? So actually, what it figures out to, if we were drawing 10 milliamps over 24 hours, it's 240 milliamp hours a day. 240 multiplied by 7 days equals 1,680 milliamps, which is 1.68 amps, just from this last week. When we add it to our conservative 2 amps last week, that gives this battery about 3.5, almost 4 amps just from this little battery. And I'll show you how big it is. So the battery is, let's say, 5.7 centimeters by 5.6 centimeters. 5.75, well, okay, 5.75. So it's only a very small area. So that equals 31 centimeters squared. So now if we go 5.5 by 5.7, 31 centimeters squared, 1.2 volts conservatively, 3.5 amps conservatively, multiplied equals 4.2 watts. So that's a 4.2 watt cell just sitting there like it is, more than likely, and that's being conservative. So as you can see, it's quite an interesting cell. Now here's the thing. I've tried a couple of other comparative cells, and this one has, well, I'll explain it to you, but this one has the anionic as well as ionic, that is potassium hydroxide with the anionic as well, so positive and negative. This one's just got potassium hydroxide, or KOH. And really both of them really did not last well, although this one was a little bit, you could charge it a little bit, this one you could charge it but really bugger all. So it made a huge difference having our anionic mixed with our ionic. So here is a batch I made. It's quite stringy, as you can see, and what it is water, a 6 molar water of potassium hydroxide and a 2% addition of the anionic liquid. So to give you an idea of how strong this anionic liquid is, what they do in industry is they add 2% and then they add that to approximately 2,000 litres of water. So it's a very minute amount that does the work. And as you can see, it's all like a jelly here. So that's very interesting. The other thing to note was that these cells really failed, really capacity-wise, because it didn't have our gunk or our silica. So I found that very interesting after meditating on it. So what I think I might do is, that might last another week, don't know. But what I might do is I might pull it apart and just find out how it looks like, because it could just be a redox reaction. Righto, this is the first time I've touched it in 2 weeks actually. Pull that out. Alright, I'll take it out and we'll have a look. Righto, so my first impressions is that it's quite dry. Even though I've sealed it in the bag, still the bag was not sealed 100%. So let's have a look. Let's see if we can get this apart. Yep. Yep. I'll come back. Okay, so slightly moist, but gee, it's pretty dry. This is the what is it? Graphite plate, and really that's really degraded that paper. So we're just going to leave that. There's really not much to see there, but we'll have a look at the zinc. I'm more interested in the zinc from the perspective of degradation. Alright, just take that off carefully. You can see that the silica is dried off on the edges. There we go, take that off. That's just the paper. And we want to take that silica off and have a look what's underneath. I'll just get a knife. Before I did that, I just did a pH test on the surface there, so it still does contain a little bit of moisture. And as you can see, it's still highly alkaline, which is the KOH in action there. All right, let's get this stuff off. Righto, so there it is without the sand, silica sand. And I don't think I put any activated carbon, which means the zinc has gone black, which would be be conducive with my other test here where the zinc has gone black. So what we'll do is we'll take it out and we'll give it a wash and just see what the degradation is. So out in the light you can actually see that it's actually not a black, it's actually a brownie, so it is the zinc changing colour. And I notice that brown colour only happens when I use that anionic liquid. So let's give it a wash and see what happens. Perhaps I'll come back when it's completely washed. But you can see in the sun, I'll show you, it's quite a brown colour. Get to the sun. There you go, it's actually quite a browny colour. So that's very indicative. Okay, I'll go and clean it off. So looking at it, you can see here in particular the high bits of zinc around at the low bits. So yeah, it does appear that there's been a degree of redox reaction. I would suggest it's like you can feel it. Doesn't seem to be a huge amount. So I'll just give it a sand and we'll have a look at it. So looking at our zinc, we can definitely see the result of the redox reaction quite markedly. Probably another 2 weeks of that sort of exposure, I would suggest it would probably fail or be consumed up totally. So we might rebuild the cell and just let it go. Further to that, I discovered quite naturally that the activated carbon that I put on here actually holds current as well. And actually increases the voltage and the capacity, that is the current capacity of the cell. So that's a combination. So whether the gunk works or it doesn't, that is to say the silica, the fine silica, it probably does, but is it going to be a world beater? No, it's not. Although 4.5 amps out of that cell is pretty impressive. But probably something you'd make as an emergency type situation. So now all I'm going to do is pour some of that into our gunk, then put it on our cell, rebuild it and then let it go again. So what the anionic does is it forces a separation of the particles of sand from the water, and so the sand agglomerates together out of sight of the water, which is very interesting. But I think it might be enough. That's what it looks like, all goopy. Anyway, we'll put it on our piece and make the cell. Should be all right, I think. I'll spread it out, and it's not sticking to there now. I'll come back when I'm done. So there we go. Coverage is good enough. All I do is put a new piece of kitchen toweling on there. Okay, kitchen toweling goes on top. There we go. I'm just going to wet it down a little bit. I'll use some KOH for this, just to wet it out. Wet the this one out as well, which is potassium hydroxide. There we go. Should be wetted out. I think that'll do. It's quite a bit. And we'll whack it on back on top. And our cell is done. Squish him down. Alright, let's just check the voltage. 1.38. Check the current. Keep it on 10 just in case. See what it's at. Okay, so not much, 168. Just change it to milliamps just to double check. Okay. 200, oh now it's saying overload. Alright, hang on. Last things we want to do is bugger it up. Alright, try that. 0.8, 0.9. Alright, so about 1 amp on there. Just a shade under. Alright, I'll put it back together in his container. There it is, back in its container, negative and positive. We've got it pretty well sealed this time, so it'll be interesting to see how long it lasts. And as you can see, wired back up there to its full capacity of shining bright. So, hope you found this video informative and interesting. That I would expect that to last the next week. I think what actually happens is while it pulls the power from the cell, the cell's rejuvenating itself faster than what the light is consuming it, and that's why it lasts such a long time, to a point where it gets to the point of pretty much degradation. So I hope you found this video useful, and catch you later.